Okay, let's start then. And thank you very much, everybody, for coming to another session of the seminar. And Tito will do the introduction this time.
All right. Okay. My pleasure to introduce Alvaro Lorca. Alvaro is a PhD student at Georgia Tech, working with Andy's son on energy topics. He's graduating very soon, right?
Yes, I hope.
And he's been doing, prior to that, he was doing some, well, he graduated from Católica in electrical engineering?
Industrial and math.
Okay. Yeah. And then also at Georgia Tech, he worked in some humanitarian logistics. One of his papers got an award. And now he's working in energy, and he'll be talking about multi-stage adaptive robust optimization for electric power.
Yeah. Thank you, Tito. Well, I'm very glad to be here. Thanks so much for having me. So Tito was mentioning some stuff about me, so most of that is here. Yes, my advisor is Andy Sun. I work on, my thesis is on robust optimization for power system operations. So I'll be talking about maybe the core or main part of my thesis. And my committee has Shabir Ahmed, Dr. Antonio Conejo from Ohio State University, Arkady Nemirovsky, and Alexander Shapiro. I was an intern at IIIO New England. They operate the power system in the northeastern US. Last summer, now I taught simulation analysis and design course. And as Tito mentioned, I have done some research in post-disaster logistics or humanitarian logistics before Georgia Tech. Okay, so I'll be talking about, let me keep track of time so I don't go too far. I guess I'll talk about 40 minutes or so. Okay, so I'll be talking about electric power systems, and to me this is a very nice area for doing operations research or operations in general things because of its complexity at the physical level and at an institutional level as well. So I'm very motivated to be working on this. And maybe the main motivation for my work this years is the wind and solar power. Basically, you want to have in your power system as much as possible of wind and solar power because they're very clean and they're very cheap, or at least costs are going down very fast. But they are very noisy, if you will. It's not clear at all how much availability of this type of energy you will have even in a very short term. Even if you have the best weather forecasting model, you won't be able to know exactly your availability. So for example, this is wind speed over a week, and you can see that there's some very strong wind drop-downs in certain time periods. These are 10-minute granularity. And these strong wind drop-downs, with speed drop-downs, map to a strong drop-down in wind power in your power system. So you want to manage your power, operate your power system in such a way that you are prepared for this type of events. So that's perhaps the key aspect we want to assess well with robust optimization. So I'll briefly go, time permits, I'll go over this outline. I'll briefly go over an introduction of the problems I'll be talking about, which is mainly unit commitment problem. Then I'll go over a robust model for the unit commitment problem. I'll discuss our efforts in solving this problem, designing an algorithm that's efficient for a large-scale power system. I'll talk about some computational experiments for this work, and then I'll talk about one important extension I've worked in the last year or so for this work, which is incorporating information on temporal and spatial correlations of wind and solar power, which we call dynamic uncertainty sets, and also incorporating energy storage, which seems to be a critical technology for being able to absorb a deep adoption of wind and solar power. And then I'll mention some other extensions of this work. Please go ahead, if anything's not clear, please go ahead and interrupt me. If anything, I skip anything or you're not familiar with the specific problems I'll be mentioning. So, okay, I'll be talking about what we call the day-ahead unit commitment, and there's the real-time economic dispatch problem. So the basic idea is, say it's 12 p.m. today or 4 p.m. today, and I want to find the schedule for the next day. I have 24 hours, starting from midnight to next midnight, 24 hours in which I want to find a schedule such as this one. So what this means is this 1 is the machine, the generator is on, and 0, the generator is off. And I want to find, this is the critical schedule I want to identify in the day ahead. This is called the unit commitment problem. And the difficulty here, of course, these are binary decisions. That's one important difficulty. But there's many physical properties of both the network. Transmission lines have a capacity for power flows. And generators, I cannot simply turn them on and off whenever I want. I will incur high fixed costs for having machines on or for turning them on. And they usually have this, if they're thermal units, say you have coal or something like this, you will basically, if you turn the machine on, you will have to have it on for a certain time. If you turn it off, you have to have it off for a certain time. There's certain thermodynamical properties that make it, that you have to take into account. So there's several constraints for how to deal with the on-off decisions. And basically what we want to do is meet demand at each node. This is how we represent the power system. These arcs are transmission lines, and nodes can represent generators or load or demand nodes or wind farms and so on. And we want to match demand at each node, respecting power flows, respecting the physical characteristics of the generators. That's the basic idea. Okay. And this is what power system operators do in the day ahead. They find the schedule, and then in the real time, typically in a 10-minute granularity or 5-minute granularity, they will solve what they call the economic dispatch problem, where they where they know what generators are on and off, and they choose or adapt the dispatch levels, the power that every generator is feeding into the system. So that's our starting point for this work. Okay, so how does a usual or traditional model for unit commitment look like? We have this XIT, which is on-off decision, and PIT would be a dispatch or power level at generator I, at an hour T, if you will, in megawatts. So the problem looks like this. I will have some fixed costs or costs for turning on machines or off, and some variable costs for dispatch levels. This X here will capture minimum up and down times and things like this. And this P will be related to X in the following way. If X is 1, then PIT, dispatch at generator I at time T, can move in a range from P min to P max, say 100 to 200 megawatts, or 10 to 100 megawatts. And if X is 0, then I cannot use the generator, of course. P is 0. Then there's this R here, our ramping capacities. This is very, very critical. So this is a constraint for the delta P, if you will, for the difference between certain time period and the next time period. It tells me how fast my generator is to change its output level. And this is critical because if we have one of these wind drop-down scenarios, I want to be able to very fast change the output of the generator to counter this drop-down in wind speeds, in wind power, if you will. So if all your generators are immensely flexible, then my work doesn't have a lot of value. But if my generators are very inflexible and they are not very fast to adapt, say you have a lot of coal in your power system, for example, coal generators are very slow to change their output levels, then this work becomes critical. You want to correctly assess how you're operating your operating your power system. This expression here are transmission line capacities. And this is a linear formulation which is an approximation of the true power flow equations. This is the common practice for this problem because of its simplicity and because it allows you to solve the problem. But we'll see there's some work here trying to really capture nonlinearities. I will mention that later. And this is basically energy balance. I want to match demands. So that's what's called the unit commitment problem, and it's what we'll look about, what we will look in this talk. Very briefly, some literature on robust optimization. This is very common in the last, or it's gaining a lot of popularity in the last 3 to 5 years, especially in robust optimization for unit commitment, but also for the real-time problem, the economic dispatch problem. And we see different models capturing different aspects, like security, for example. If transmission lines sometimes can fail, some robust optimization models have captured these aspects. There is some work for economic dispatch. There's a lot of two-stage approaches with load uncertainty, where the basic framework is I will make my decisions of what generators will be on and off. Then there will be some uncertain demands or wind or something like this revealed. And then I will make my dispatch level decisions. So it has a two-stage structure. And we will see as we will go beyond this two-stage model into a multi-stage formulation. I will go into a little more details. And there's some other ideas. There's even some work on affine policies, and this is actually what we will dig into a little bit more. Okay, but I don't want to spend too much time on literature. Okay, so what I'm here to talk about is this. So I just mentioned this two-stage model. Okay, so this is what's called adaptive robust optimization. It means I have some set of what you could call first stage or initial decisions, and then some set of adaptive decisions that as uncertainty is revealed, I can adapt to these parameters. So this basic min-max-min structure here, people have used it for the unit commitment in the following way. This X is again my on-off decisions. There's some fixed cost related to it. Then this D in D here means that loads, and when I talk about load, you can think of demand minus wind power minus solar power. You can think of wind power and solar power as negative demand. And we capture all of this into load. So okay, then you can think of loads are revealed in some worst case way, and then I have this recourse action, or based on this information of my choice for X and some adversary's choice you can think of for D, I will make a best decision for dispatch levels. Okay, so that's basic framework. And there's good algorithms for solving this problem, and it has been shown that this can incur a lot of value for the true problem in terms of finding a decision X that is very well prepared for variations in this parameters D that I don't know exactly what they will be. I can have a forecast, but there will be some error, and this model is very good at capturing that. Okay. Now the issue with this model and why we want to go beyond it is that when you're designing your decision P, you're deciding it over 24 hours. And you're basically assuming that at time when this vector D is revealed, I will know it before I make the decisions for these 24 hours. So you can think of my decision P at time 24 or at time 1, knowing what demand will be at time 24. These are whole vectors for 24 hours. And this is perhaps not a very good assumption, because if I make some decision at time 1, assuming that something will happen at time 24, maybe I'm not well prepared for a change at time 24. So you could think of this model as, if you're familiar with stochastic optimization, as ignoring non-anticipativity constraints. So what a multi-stage model looks like is as follows. It's the one here. Instead of finding a vector P that knows all of D, I will find a function P, okay, and there's some P at time T, vector of outputs at time T, only knows the information revealed up to time T. And we have this notation here, D brackets T, that represents the vector of demand up to time T. So what I want to find is my schedule X of 0, 1 decisions, on-off decisions, and a function P for dispatch levels that, as information D is revealed, tells me what to do with my output decisions. The difference between this model and the second model and first model is that you can write actually the two-stage model in this functional optimization problem format, where P at time T depends on the whole vector D. That's the whole difference. And that's an easier way to see that the two-stage version of the problem is just non-anticipativity is ignored. Okay? So this is basic framework of the problem we are addressing. And we will see that actually capturing this multi-stage format or non-anticipativity allows you to prepare better your capacities against potential variations in what you expected in your forecasts, if you will. Okay, and I will try to dig a little more insight with the experiments. Okay, so we want to solve, okay, so how does it look for our unit commitment problem? We want to find this function P, so, that contains these decisions PIT, generator I at time T. depends on the history up to time of demands up to time t, and we have the same constraints I showed you before. Okay, and the uncertainty set we will choose to capture these potential realizations of demand or net load will be the following one. You have some at each time t, you have a different uncertainty set, and at time t, the uncertainty set is as follows. There's some djt bar, which is a forecast for net load at node j at time t, okay? And there's some variability factor, if you will, the hat, jt, which could be like a standard deviation times some security factor or something like this. And people usually use this budget of uncertainty, which comes from a central limit theorem argument, okay, which gives a better shape to the answer, a more realistic shape for the uncertainty set. I don't want to dig into too many details. This is a widely used uncertainty set. It's a budget uncertainty set. And so far, what I will show you is our work with this simplest, if you will, or common uncertainty set. And later, I will discuss the implications of using a much better uncertainty set model, which is part of the work as well. But we will start with this one. Tito? Yeah.
One thing that is this uncertainty set doesn't capture the dependence across time.
That's a very good point. It doesn't capture the dependence across time. You can think of a good model for an independent process across time, because these are different uncertainty sets for each time period. And actually, that has a problem, because you can think of your adversary giving you a trajectory of demands where demand goes from some extreme high value to some extreme low value to some extreme value. It doesn't capture that. And I will dig into that at the end, how we adapt everything to a better uncertainty set that captures that. So actually, thank you for the question.
So, in a robust context, I imagine that the worst case is always taking the higher demand, for example.
That's a very good point. So you can think of DJT always taking this highest value, right? However, this is a big power system, and we're not allowing all of them to take the highest value because of this budget of uncertainty. Because that's a lot more realistic. So then the issue is, your adversary, if you will choose the worst location for the highest values based on some transmission issues. Actually, if your transmission is unlimited, if your transmission is congested, this will have a lot more value. And that's what we see from experiments, from simulation experiments. Yeah. Okay, so why do we care about this multistage model? I mentioned a little bit about it, but basically, we have this result. Again, I mentioned, if there is no ramping constraints, all the generators are extremely fast, then actually both models give you the same optimal solution for your decision on-off decisions. Okay, and basically that decomposes the problem into the inner problem into multiple time periods. Okay, and we have simple examples where we show that this is one of them, where we show that if you find the solution from the two-stage problem, ignoring non-anticipativity, this can actually be infeasible in the true multistage problem. Because this is very natural, because this two-stage problem is a relaxation, where you're relaxing and you have a larger functional space, if you will. So in a way, if you solve the two-stage model and you think you are prepared for all of these variations, you're not really prepared for all of these variations in the practical real-world problem. Okay, so I should speed up. Yep, sure.
I was curious about the result of the theorem.
Yep.
They are equivalent, so...
yep, they are equivalent.
So without the represents, it's the same thing? Because
yeah.
Some intuition why.
The idea is basically, if you look at this, I don't have... Okay, if you think of this problem, if this omega here doesn't depend on pt minus 1, it breaks the problem into t time periods. Because as well, you're also using that the uncertainty set is separable here. Yeah. Yeah. So it's the simple structure that leads to that. If we add here energy storage, this is no longer true, because energy storage will connect different time periods. Yeah. So yeah, we wanted to basically get a little more insight into what's the critical difference, if you will, between these two models. Yeah. And actually, the two-stage model has gained a lot of popularity. All the power system operators in the United States are very, very aware of this research, and they have different researchers doing more work on this. So that's why we wanted to study basically, okay, this is very popular. It seems it really has some value. Can we go a step beyond capturing a little bit more finer details, this hour-to-hour process, if you will. Okay, so this is our problem, multi-stage problem. And how do we, this is a functional, on a functional space, right? This min-max-min structure you can exploit somehow, but you can actually write this problem as a min-max, 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 min structure, and so on. Okay, the way to go here is, or the tractable approach we built here on the work by Bental, Gorshagos, Litziger, and Nemirovsky is to restrict yourself to a simpler functional space. So we will lose a lot of power, well, a lot of flexibility, if you will, but we will allow to find at least a feasible solution. And numerically, we can see if this is a good solution or not for the true problem in the functional space. So what we do is we restrict our functional space to this linear form, linear dependence structure. Okay? Okay, so that's the problem we want to solve, multi-stage, robust unit commitment with affine or linear decision rules, affine policies or linear decision rules. Okay? So if I give you that problem, the first thing you would do, if you're digging into this, is you would actually use what we call the duality-based approach or duality reformulation, which is traditional approach. However, this absolutely fails in practice. We can solve tiny problems with 3 generators or so on with this method. So what we do instead to actually solve the problem for large-scale power systems, we combine constraint generation as a specific simplified form of affine policy, not the general form. We exploit the structure of this policy, and we do some ideas to make the algorithm go faster, to deal with the binary variables. Okay? Okay, so why does the duality-based approach fail here? If you think of a robust constraint, all you want to do, this C here will depend on your decisions, and H will depend on your decisions. So think of maximum output of the generator. That's a robust constraint. I want to find a function such that under any realization D, my generator doesn't generate more than 100 megawatts, because that's its capacity. So this H would be 100, for example, with some other variables. So this is a robust constraint, and here our D here is a polyhedron. So you can write this problem as follows, where ED less than or equal to B is the description of the polyhedron, and what you can do is take the dual here, and then you see that this robust constraint, which is actually an uncountable number of constraints, you transform into this finite system where there's new variables, pi. Okay, that's the traditional way to solve robust optimization problems. The problem is we obtain a huge mixed integer program because D, especially if D is high dimensional. Okay, because you are basically transforming all of this representation of D, this high dimensionality here translates into high dimensionality in this representation, this dual representation, if you will. So actually, for a very small, for a medium-sized problem, we obtain more than 100 million variables. So this is actually not efficient. However, if you take this huge reformulation and you think of a Bender's decomposition algorithm, what you end up obtaining is something you can think of more directly for the problem. You can actually look at the problem with the robust constraints and think of, okay, let's start with a simple representation of my uncertainty set and build it as needed. And that means that we will add these constraints one by one, depending on what we need. And we will need some oracle to separate over the uncertainty set. And for a robust constraint, see what realizations of the uncertainty set are leading to infeasibilities. Okay, so the idea is this. I have a master problem. These W's here are determine my policy or my dispatch levels at generators as a function of demands. And instead of assuming the whole D, this is a one robust constraint, the kth robust constraint, if you will, I will have a set or a list dk of just some points from the uncertainty, some bad scenarios. So for example, for some robust constraints, it could be that if loads are very high in this part of the power system, this leads into some problem in a transmission line that will carry too much flow. So I need to add that point to my representation, and I build the problem as we go on. So that's the idea. So we start with some empty decays. We solve the master problem, just this problem, without any robust constraint, and then we see my policy to what constraints, to robust constraints, is leading to infeasibility. So with this policy, this generator under this scenario is generating more than 100 megawatts. So I will add this scenario as a constraint, and now I will solve it again, and I will keep doing this. And every time I find a new policy, I will check all of my robust constraints to see what scenarios are leading to infeasibilities. Okay, so this is the idea. Instead of considering the whole D, we build it as we go on. That's the whole idea. Okay, so it's a constraint generation algorithm to solve the problem. Okay, now if you take the general affine policy, it would look like this: generation at generator I and time t. There's some fixed decision, WIT, and some sensitivity factor, WITJS. So DJS would be the demand at node J and time S. Okay, and what we're saying is this decision at time t will depend on all the realized net loads or demands at all nodes and all previous time periods. This is the most general function that respects non-anticipativity, and it's linear, of P as a function of D. However, if we do this, if we try to solve for this problem, constraint generation algorithm becomes extremely unstable. Okay, so we actually need to go for a more humble objective, if you will, and simplify this function. So you can think of actually the policy we end up solving or studying more thoroughly is this one. What we're saying here is your generation at generator I and time t will only depend linearly on the total demand in the power system at time t. So I will take all the demand from all of these nodes, add it up, and this number, this overall system-wide demand level, will be my variable factor I will consider here, and I will only have this simple sensitivity factor. So if demand, system-wide demand is instead of 10 gigawatts, 11 gigawatts, this W will tell me what to do with this generator. And you can actually think of simpler forms. But this one, we can actually exploit the structure of the problem to reformulate many of the robust constraints using this particular form. Okay? So I don't want to go into all of the details. We will have the paper for that. But this is the idea. If you look at this policy and this constraint, for example, these are the most critical constraints, not generating more than some Pmax level. If we use the simple policy, we can reformulate all of this robust constraint, where uncountable number of constraints, into just two specific constraints. I only need from the uncertainty set, what point in this uncertainty set generates the highest level of total demand and the lowest level of total demand. If I find only these 2 points, these two extreme points for my polyhedron, this is enough to characterize the whole robust constraint. And we can do something similar with ramping constraints because of the separability of the uncertainty set into different time periods. Okay, so this is the key to making to end up using constraint generation only for some transmission system level constraints, such as transmission flows. Okay.
Why is this paper?
Yep.
Why the minimum is relevant?
So okay, so you want to find. So basically, okay, so if you look at, you can basically replace this robust constraint where there's some polyhedron here by the extreme points. By all the extreme points of this, that's very easy to prove. You only need the extreme points of the uncertainty set because it's.
I get that, but
okay.
If you look at the inequality, if it satisfies for the higher, this would imply that it is also satisfied by the smaller.
No, I'm not saying that. No. So suppose that your uncertainty set is set for all the nodes of your power system, but we're aggregating things. This policy aggregates things. So just the policy. Now, we will still respect all the constraints at a nodal level, but at node level. But But if you look at this expression here, you can prove that you only need actually 2 extreme points, not this uncountable, or this large number of extreme points. You only need.
Why do you need just 1?
No, we need 2. These are 2. Yeah, the maximum and the minimum.
Why?
Because you're basically projecting everything into this aggregated level. And basically, if you have this satisfaction here, then any other extreme point will be in between these 2 levels. If you look at the output at total demand, at maximum total demand, and the output at minimum total demand, suppose these are 100 megawatts and 150 megawatts, then any extreme point will be in between.
So the capital W and T are allowed to be negative.
Yes, they are. They are. We rarely see that. We haven't. We actually tried to prove that the W is always positive, not negative. We weren't able. Yeah. But that's not a problem. You can have negative W's. And in some experiments, we've observed them. Yeah. So that's the idea. And then we have some simple techniques to handle the binary variables. So if you think of Bender's decomposition method for a problem with binary variables, you can actually use callbacks to do a branch and bound process and the cuts in one tree, if you will. Or a simple technique, we've tried both, is to fix your solution, your binary decisions, then apply the constraint generation process for all the other variables, and only when that converged, go back to changing the binary decisions. And this reduces the number of mixed integer programs we have to solve across the algorithm, and then actually makes it a lot more efficient. So those are the ingredients of the algorithm. Let me briefly go over. I should take about 10 more minutes. So let me briefly go over the impact of this model, why we care about this model, and just briefly mention some extensions. So we studied these questions. Is the algorithm good? Is this simple affine policy good? Is it a critical model or not compared to the 2-stage model? Is it some rare thing, or is it something you could observe? And simulation results to see if this is really has some impact over traditional methods. Okay, so the algorithm is efficient. All of these techniques I showed are critical to make it work. We can actually solve a medium-sized problem in less than 3 minutes, and a large-scale power system. This is actually Poland. It has about 300 generators. We're taking 100 transmission lines in less than 4 hours. And in more recent experiments, we've pulled this actually about 2 hours.
So the gamma is
Oh, so sorry. Thank you, Tito. Yes, this gamma is a critical aspect that is what you can tune in your robust optimization model. And if gamma is 0, you're just taking a deterministic problem where there's just a forecast. And if gamma is large, you're increasing your uncertainty set.
Is that something for what's called delta?
This gamma goes inside this delta and inside this variability factor. Yeah, this variability factor is gamma times standard deviation from data. Yeah, so gamma grows your uncertainty set. Thank you. Yeah, that's very important. Yeah. Okay, so how do we know if we have a good affine policy or not? We need a lower bound for the true multistage problem in a functional space. So this is our policy here. This is a general affine policy. This is the true functional space problem. This is the relaxation, which is the 2-stage robust, you see. And people actually cannot solve this problem for large-scale systems. They solve an approximated version. So, however, that approximated version, we can tune things a little bit here, can give us a lower bound for this relaxation. So this is actually the lower bound we use to measure how good our solutions here are. So this is the optimality gap I will show. And surprisingly, we achieve very good, very, very small numbers. Okay, for the large-scale power system, if you use this WIT policy with the structure I showed you, we obtain, usually what you want to have is gamma around 1.5. I will show you why in these experiments. But for gamma equals 3, which is very conservative, very, very large uncertainty set, we obtain some number below 1%. If there's a lot of transmission congestion, this number will be higher. So we want to go beyond this simple policy. But for what you could call reasonable conditions, we obtain good quality. Surprisingly, because it's a tremendous reduction of complexity, if you will, or tremendous reduction of the functional space. And if we compare the multi-stage and the two-stage models, if you take the solution from the two-stage model and see how well it performs in this more realistic multi-stage model, it actually doesn't perform well. It's not some rare pathological thing. It's a practical thing. Okay, and I'll skip details here. And this is what's critical for the power system operators. Okay, why would they care about this robust model if they are using these traditional deterministic models? And what they do is they choose reserve levels. They deterministically, they have some rules for choosing reserves and distributing reserves. So I have some forecast, but I will have 500 megawatts extra at a system level in case something happens. And this is the sort of rules they use, and they might distribute this reserves or something like this. But this is a systematic way to assess uncertainty, if you will. Why would they care about this? What I show here is simulation results for multi-stage and two-stage models, but both of them outperform in both cost effectiveness and reliability the deterministic models. And they are aware that this outperforms deterministic models. So what we're showing here is how the multi-stage model can outperform the two-stage model. So what we have here is this. For each different possible gamma in some range, we solve both the two-stage model and the multi-stage model, and then simulate what would happen with the power system if you use this or that solution. Okay, so we simulate the real-time process in a very realistic way. We mimic what would happen to the power system. Okay, and I'll skip details, but you can ask me later. And we look at things like cost average, cost standard deviation, or how stable costs are, if we were able to, these penalty measures, if we were feasible or not. Okay, and how often we were feasible or not. And what we see that if you wisely choose your uncertainty set size in such a way that it's not too conservative, so gamma equals 3 is very conservative, but also it's safe enough, you can actually obtain about 0.5% reductions in costs, in average costs, and a much more stable behavior of the system. Okay. So as a summary of this work, this is first multi-stage robust approach for unit commitment. We explore this idea of simplified affine policies, built efficient constraint solution method using constraint generation, and our experiments show that there's some potential advantages in practice. Okay, and our paper is in third round review in operations research. Sorry, this is this work with my advisor Andy Sun and Eugene Litvinov and Tongxin Sheng, who were I was working with them at IIIO New England last summer. So they are well aware of this work. And this is under review at our operations research, and we hope it will be out soon. But it's available in case you want to take a look in Optimization Online. Okay, so briefly, a couple minutes, 5 minutes or so, I'll go over some challenges and work we've done and work we are to do at some point. So the idea is this. What I'm showing here, this is from another paper, it's here, where we just looked at the real-time problem. This paper is published in IIIO Transactional Power Systems, and we looked at a robust model for the real-time problem, just for the dispatch problem, where we assume the on-off decision is fixed. And what we saw here is even in the real-time problem, robust optimization can help, and if you capture temporal and spatial correlations somehow in the uncertainty set, you can actually obtain practical benefits. I don't want to go into details here, but we can show that assuming this information can outperform ignoring this information, or assuming independence, if you will, under real data, both in terms of cost effectiveness and reliability, again, which is what power system operators care about. And the goal here is exactly that wind and solar power present strong both spatial and temporal correlations. So the challenge for us is incorporating this information into the unit commitment model. Okay, and here's where we want to go beyond this independence assumption we built the algorithm on, and what I showed you before. So we do care about that, and let me just show you briefly how we capture temporal and spatial correlations in an uncertainty set. So here we're looking at more details. Before I used this DJT, which was load, so demand minus wind minus solar. And the underlying assumption there is that we're ignoring the fact that you can curtail wind and solar power. And the fact is, if you have a power system with a very, very high presence adoption of wind and solar power, you will need to curtail it. I was just in a conference, IIIE conference, this professor from China was saying China curtails about 10% of its wind because it's not able to absorb all of it. For reliability, it needs to curtail wind. So now we assume that the fact that you are allowed to curtail wind, and we build an uncertainty set specifically for wind and solar power. Okay? So PAT here, PATR bar, is available power at some renewable units, I at time t. So this renewable unit can be wind or solar. And what we do here is we have this linear form, F and G are seasonalities or things like this, and this U absorbs the uncertainty. Okay, and this U at time t depends on previously realized U's and some new information V, some other uncertain component. This structure can remind you if you're familiar with vector autoregressive processes, which is the most basic statistical model for capturing both temporal and spatial correlations, if you will. So what we do is we take a vector autoregressive process and fit a usual or some sort of uncertainty set, which is some norms form here for this white noise process, if you will. And actually having this ends up giving us an uncertainty set that captures these dependencies. So if these A's are 0, they are not here, and this B is diagonal, we recover the previous form of uncertainty set, which ignores both temporal and spatial correlations. If B is allowed to have off-diagonal elements, then you can actually capture spatial correlations, and if these A's are here, you can actually also capture temporal correlations. Okay, and fitting from a vector autoregressive process, we can obtain here a good model for these dependencies. So I don't think I have time to go into details of how we actually are able to build a new algorithm that takes this into account, also when we consider energy storage decisions. But the main challenge is to reformulate the robust constraints in a different way. Okay, and that's where the work we've done here. I don't want to go into details because of the time. But we can see that if we do capture temporal and spatial correlations, we can actually go one step beyond the multi-stage robust UC with what we call static uncertainty sets that ignore temporal and spatial correlations. So we do the simulations again, but with a very realistic process for wind and solar power, and see that your solution, if your uncertainty set captures this information, you can actually find a better decisions for the power system. Again, in terms of effectiveness, of costs, and reliability.
But it's very important the construction of the matrix A, right?
Exactly.
How do you work on that from the data?
So we take data and we fit this vector autoregressive process. So we use statistical techniques to get the best version of these parameters. So there's a maximum likelihood argument there from data. Now we have a statistical model, and from that statistical model we build an uncertainty set. So our uncertainty set is built on this statistical model. But the techniques we use to build a statistical model are known statistical techniques. Yeah. For time series that capture different components in time. Yeah. So okay, yeah, we can actually do a little better. And there's some nice synergy with energy storage as well. We can show that if we capture this information, you can use better your storage units. Okay, so this is the idea. We have a working paper. If you're interested, I can share it. Yeah, and we should be submitting this very soon. Briefly, other extensions. One challenge is capturing binary recourse. So in practice, you have generators that are very, very fast to turn on, and some power systems are actually discussing the idea of incorporating 4-hour ahead markets, where you will basically be able to adapt your on-off decisions in the real time, if you will, or in the hour-to-hour process. And capturing this information means that we will have binary recourse decisions or adaptive on-off decisions, and that's very hard to incorporate into this problem. And what we aim to do here is use some ideas from finitely adaptive robust optimization. Another extension is actually going beyond this simple WIT policy I showed you. This can be very important when there's high transmission congestion. If you think of a more complicated policy like this, where you actually care about demand high here or demand high there, our algorithm is very unstable for solving this type of policy. But we are actually thinking, this actually came from Dr. Nemirovsky's first idea. He said your algorithm is very similar to level bundle methods. And the idea is in level methods, you can actually add stability to a cutting plane approach by somehow finding a policy or a solution that's not too far away from some stable solution, and so do this process. So we have some ideas for actually doing this. And finally, as I mentioned before, we're using what's called a DC power flow approximation, which is a linearization of the true power flow equations. But power system people are very interested in using the true nonlinear formulation of the problem instead of solving a proxy and then adapting as we go. If you're able to really capture nonlinearities, which are very complicated, in particular non-convex, then you can find much better solutions. And we have some ideas for using something that's better than the linearized format, using a second-order cone relaxation. And we have some ideas for solving the problem in this case. And that's what I wanted to talk about today. Thank you so much for your attention, and feel free to contact me if you're interested in anything here. Thank you for your attention. Yeah.